It's not a comet. It's not a solar flare. It's not some distant threat, drifting in from the edge of the solar system, decades away, giving us time to prepare. It is a mountain of rock, roughly 1.5 kilometers across, moving at tens of thousands of kilometers per hour, and until October of 2022, nobody on this planet knew it existed. Its name is 2022 AP7, and it wasn't hiding in the dark, it was hiding in the light. Here's the part that should stop you cold. We didn't miss it because our telescopes are weak. We didn't miss it because we weren't looking. We missed it because it was sitting in the one direction we physically cannot look, straight into the glare of the sun. For years, this object crossed and recrossed a region of space that our survey telescopes are effectively blind to. It was there the entire time, we just couldn't see it. And astronomers openly admit there may be more. Today, we break down everything about the asteroid NASA-funded surveys found hiding in the sun's glare. What it is, where it came from, why it took this long to find, what would actually happen if an object this size hit Earth, and what comes next. No filler, just the facts. And a warning before we go further. Everything in this script is attributed. Every number comes from a published paper, a named observatory, or a named scientist. Where the science is uncertain, we say it's uncertain. No guessing, just the facts. Start with the discovery itself, because the how matters as much as the what. The object was found by a survey led by Scott Shepard, an astronomer at the Earth and Planets Laboratory of the Carnegie Institution for Science in Washington, D.C. The instrument was the Dark Energy Camera, DCAM, a U.S. Department of Energy-built camera mounted on the Victor M. Blanco 4-meter telescope at NOAR Labs' Cerro Tololo Inter-American Observatory in Chile. The findings were published in the Astronomical Journal on September 29, 2022. This is not a rumor, not a leak, not a viral post. It's a peer-reviewed paper with a date on it. And Shepard's own description of what they're doing is worth hearing precisely. He says the Twilight Survey is scouring the area within the orbits of Earth and Venus for asteroids, and that so far they've found 2 large near-Earth asteroids about 1 kilometer across, a size he says they call planet killers. That's the term. It comes from the astronomer who found the object, not from a headline writer. Now, understand the mechanism, because the mechanism is simple, and it's the whole reason this object stayed invisible. Almost every asteroid we've ever discovered was found the same way. We point a telescope away from the sun, into the dark half of the sky, and we watch for a faint dot that moves against the fixed stars. That works beautifully. It's how we've cataloged well over 1 million objects. But it only works for asteroids that are, at that moment, on the far side of us from the sun, lit up like a full moon, hanging in dark sky. An asteroid whose orbit keeps it mostly inside Earth's orbit is never in that position. From our vantage point, it sits in the same patch of sky as the sun. It rises with the sun and sets with the sun. It's in daylight. And a 4-meter telescope pointed anywhere near the sun during the day sees nothing but blinding sky, assuming you don't destroy the instrument trying. So the survey team did the only thing that works. They hunted in twilight. 2 windows a night, roughly 10 minutes each. That's it. 10 minutes after sunset. 10 minutes before sunrise, when the sky has dimmed just enough to reveal something faint, but the sun hasn't dropped so far that the target has already set below the horizon. And it gets harder, because you're looking near the horizon, you're looking through the thickest possible column of Earth's atmosphere, the maximum amount of air between your mirror and the object. Shepard describes the problem directly. You need large areas of sky, because the inner asteroids are rare. You need deep images, because asteroids are faint, and you're fighting both the bright twilight sky and the distorting effect of the atmosphere at the same time. Every one of those factors works against you simultaneously. That's what a blind spot actually is. Not negligence, physics. So what did they find in it? 2022 AP7 is estimated at roughly 1.5 kilometers across. Different reports of the discovery give a range of about 1.1 to 2.3 kilometers. Because we don't have a spacecraft alongside it, or a radar echo, we're inferring size from how much sunlight it reflects. And that depends on how dark the surface is. A very dark rock that's large looks the same from here as a brighter rock that's smaller. That uncertainty is real, and it's stated in the reporting. Mark it as uncertain. What isn't uncertain is that it clears 1 kilometer, and 1 kilometer is the number that matters. The Discovery team described it as the largest potentially hazardous object found in the previous 8 years, and likely in the top 5% of the largest potentially hazardous asteroids known. Think about what that means. We have found something like 2,500 objects that carry the formal, potentially hazardous asteroid label. This one landed near the top of that list. In 2022, decades into the modern era of asteroid hunting, discovered in a 10-minute window in the wrong direction. Now, the phrase potentially hazardous asteroid is where almost every headline goes wrong, so let's be exact. It is a technical classification, not a prediction. An object earns it by meeting 2 criteria. It must be large enough to matter, brighter than a certain threshold, which for typical surfaces means roughly 140 meters or more, and its orbit must bring it within about 0.05 astronomical units of Earth's orbit. That's about 7.5 million kilometers, roughly 19 times the distance to the Moon. That's it. Size and geometry. Nothing in that definition says an impact is expected. Nothing in it says an impact is even likely. And on that question, the discoverer has been blunt. Shepard said the object will stay well away from Earth, and that it has no chance of hitting Earth currently. There is no evidence it will ever impact us. That is the scientist who found it, saying it in plain language. So why does the object still matter? Because of the geometry, and the geometry is genuinely strange. 2022 AP7 crosses Earth's orbital path. That's the part that makes it hazardous by classification. But an orbit crossing is not a collision. 2 roads crossing on a map doesn't mean 2 cars meet at the intersection. The timing is everything. And right now, the timing is almost comically in our favor. It crosses Earth's orbit at a moment when Earth is on the opposite side of the Sun. Every single time. The asteroid arrives at the intersection, while we're 400 million kilometers away, on the far side of the star. It takes roughly 5 years to complete one orbit around the Sun. That 5-year period is what locks the pattern in place. The 2 clocks stay out of phase, and reporting on the Discovery describes that pattern continuing for centuries, not decades, centuries. Here's what this means. But over long timescales, that phase relationship slowly drifts. The asteroid's orbital motion gradually shifts to be more in sync with Earth's, and eventually it starts crossing our path closer to where we actually are. Shepard puts that shift centuries into the future. And critically, we don't currently know the orbit precisely enough to say how dangerous it could become. That's not evasion. That's an honest statement of measurement limits from the people holding the data. Which brings us to the thing that separates real planetary defense from science fiction. An orbit is not a fact you look up. It's a fit to observations, and every fit has error bars. When an object is first found, we have a short arc, a handful of positions over a few nights. From that, the software produces a solution that describes where it goes. But the arc is short, so the solution is loose, and the further into the future you project it, the wider the uncertainty spreads. Not a line, a cone. Every additional observation tightens that cone. Old images that turn out to contain the object, precovery data, tighten it dramatically, because they extend the arc backwards by years. This is why asteroid risk numbers famously go up before they go down. It's not incompetence. It's a shrinking uncertainty region. Early on, that region is enormous, and Earth is inside it, so the probability of impact is small, but non-zero. As the region shrinks, one of 2 things happens. Either Earth stays inside a much smaller region, and the probability climbs, or Earth falls outside it, and the probability collapses to 0. In virtually every case in the history of the field, it has been the second one. For an object like 2022 AP7, discovered in the Sun's glare, this is a problem with teeth. You cannot simply go back next week and observe it again. You have to wait for it to reach a favorable position, and favorable positions for inner solar system objects are rare. Refining the orbit takes patience measured in years. Now let's answer the question that's actually driving your attention right now. What does 1 kilometer of rock do? Start with what we know it doesn't take. In February 2013, an object roughly 20 meters across entered the atmosphere over Chelyabinsk, Russia. It never reached the ground intact. It detonated in the air, and the shock wave shattered windows across the city. Around 1,500 people were injured, almost all of them by flying glass, many of them because they went to the window to look at the bright light in the sky. 20 meters. No crater, no impact. Just an airburst and broken glass, and 1,000+ people hurt. Now go up. In 1908, over the Tunguska region of Siberia, an object estimated at somewhere in the range of 50 to 60 meters exploded in the atmosphere. It flattened an estimated 80 million trees across roughly 2,000 square kilometers of forest. Again, no impact crater from a primary body. An airburst. If that had occurred over a major city instead of empty taiga, that city would not exist. Hold that in your head, then scale up again. From 20 meters to 50 meters, the destruction goes from broken windows to 2,000 square kilometers of flattened forest. In 2022, AP7 is not 50 meters. It's roughly 1,500 meters. Energy in an impact scales with mass and with the square of velocity, and mass scales with the cube of diameter. Triple the diameter, and you multiply the energy by roughly 27. Go from 50 meters to 1,500 meters, 30 times the diameter, and you're multiplying by something on the order of 27,000. These numbers stop meaning anything to human intuition very quickly. That's the point. An object this size doesn't airburst. It doesn't slow down in any meaningful way. The atmosphere, from its perspective, is a thin film. It arrives at the surface, essentially at full cosmic velocity, and the entire kinetic energy of a mountain, moving at tens of kilometers per second, is deposited in seconds. Shepard described the consequence directly. A near-Earth asteroid of 1 kilometer or larger would have a devastating impact on life as we know it. Dust and pollutants would fill the atmosphere for years. The planet would cool. Sunlight would be blocked from reaching the surface. He called it a mass extinction event, like hasn't been seen on Earth in millions of years. Here's what this means, and it's the part people consistently get wrong. The crater is not the danger. If you live 1,000 kilometers from ground zero, the crater is irrelevant to you. What kills at global scale is the atmosphere. The impact vaporizes rock, both the asteroid and the ground it hits, and throws enormous quantities of pulverized material into the upper atmosphere. Fine particles at high altitude don't settle quickly. They spread, they circulate, and they form a veil. That veil reflects sunlight back into space before it ever reaches the ground. Surface temperatures fall, and the thing that fails first isn't temperature comfort, it's photosynthesis. Reduce the sunlight reaching the ground, and crops fail. Not in one country, globally, in the same growing season. Plankton production in the oceans drops, and the base of the marine food web goes with it. The mechanism that kills is not fire, and it is not blast. It's a failed harvest, everywhere, at once, for consecutive years. This is not speculation about physics we don't understand. This is the reconstructed sequence of the Chicxulub event, roughly 66 million years ago, and that object is estimated at around 10 kilometers, several times the diameter of 2022 AP7, and therefore in the range of hundreds of times the energy. So be precise about scale. An object of AP7 size is not a Chicxulub. It is very likely not the end of our species, but it sits comfortably in the range where global agriculture is disrupted for years, and modern civilization has never been tested against that. That's what the term planet killer is really pointing at. Not the destruction of a planet, the end of a growing season, repeated. Now, the honest counterweight. And this matters, because doom without context is just noise. Independent modeling of an impact by an object at the upper end of AP7's estimated size range, using standard assumptions of a typical impact speed around 17 kilometers per second, a typical 45-degree impact angle, and dense rock composition, produces something devastating locally, but short of literal planet destruction. Reporting on that modeling described the immediate local effects as devastating, while noting the name oversells the outcome. So both things are true simultaneously. This is genuinely among the most dangerous classes of object we track, and the phrase planet killer is doing more emotional work than physical. Hold both. That's what it means to follow the facts instead of the headline. Now zoom out, because 2022 AP7 wasn't found alone, and the other discoveries tell you more about the blind spot than AP7 does. The same Twilight survey turned up 2 additional near-Earth asteroids, 2021 LJ4 and 2021 PH27. Both of those orbit entirely inside Earth's orbit, which means they don't cross our path at all and pose no impact risk. But 2021 PH27 is remarkable for a different reason. It holds the record for the shortest known orbital period of any asteroid. It is deep in the sun's gravitational well, whipping around the star faster than anything else in the catalog. That's the real headline hidden underneath the scary one. 3 objects, Same blind spot, found in 10-minute windows, all of them there the whole time, and the scale of our ignorance in that region is quantified. Shepard noted that only about 25 asteroids with orbits completely inside Earth's orbit have been discovered to date, specifically because of the difficulty of observing near the sun's glare. 25, out of a catalog of over 1 million known asteroids overall. That's not a survey. That's a rounding error, so how blind are we really? Here the numbers are actually reassuring, and it's important to say so. Scientists estimate there are roughly 1,000 near-Earth objects larger than 1 kilometer in size, and surveys over the past decade have found about 95% of them. 95% of the true civilization-scale threats are cataloged, tracked, and confirmed not to be on a collision course in any near-term window. Sit with that for a second, because it's one of the quiet triumphs of modern science. A species that couldn't reliably predict the weather 2 centuries ago has now inventoried the overwhelming majority of the objects capable of ending its civilization. That happened within a single human lifetime. But 5% of 1,000 is 50. 50-kilometer scale objects, unaccounted for. And Shepard's assessment of where they are is specific. There are likely only a few near-Earth asteroids of similar size left to find. And those large, undiscovered asteroids likely have orbits that keep them interior to the orbits of Earth and Venus most of the time. Read that again. The ones we're missing are missing for a reason. They're systematically concentrated in the exact region we cannot survey. The remaining unknowns aren't randomly scattered. They're clustered in the glare. And here's the uncomfortable corollary. An object on an orbit like that doesn't approach from the dark sky where we'd see it coming. It approaches from the direction of the sun, a daylight approach. The warning time for an object we haven't already cataloged, arriving from sunward, could be measured in days. Possibly less. That's not a hypothetical. In Chelyabinsk, in 2013, on the same day that a completely unrelated, well-tracked asteroid made a widely publicized close pass, the Chelyabinsk object arrived over Russia with zero warning. Nobody saw it coming, because it came out of the morning sun. The world's telescopes were pointed at a known object, while an unknown one detonated over a city of 1 million people. 20 meters. And we had no notice at all. So the question stops being about 2022 AP7 specifically. It becomes, what do we actually do about the blind spot? The first answer is, stop being blind. And that's already in motion. The reason this survey exists at all is that DCAM can cover large areas of sky to depths that smaller telescopes can't reach. Shepard's own description of why it works is that it lets them go deeper, cover more sky, and probe the inner solar system in ways never done before. The tool made the discovery possible. Better tools make more discoveries possible. That's the logic behind the next generation of survey instruments. Ground-based wide-field surveys are moving toward imaging enormous swathes of sky repeatedly, night after night, building a moving picture of the solar system rather than a series of snapshots. The step change isn't just sensitivity, it's cadence. When you re-image the same sky every few nights, an object that moves reveals itself automatically, and the software finds it without a human ever looking at the frame. And for the sunward blind spot specifically, the answer is to leave the ground entirely, and to change what you look for. An asteroid in visible light is a dark rock reflecting a small fraction of the sunlight that hits it. That's why it's faint, and why it drowns in twilight. But that same rock absorbs sunlight and re-radiates it as heat, and in the infrared, it glows. A dark asteroid is actually easier to detect in infrared, not harder, because the darker it is, the more it absorbs and the more it emits. That inverts the entire problem. And infrared observation also gives you a much better handle on true size, which directly attacks the uncertainty we discussed earlier. The reason AP7's diameter is quoted as a range rather than a number. Put an infrared telescope in space. Position it where it can survey the region toward the sun without the atmosphere and without daylight, and the blind spot starts closing. That is precisely the reasoning behind NASA's dedicated Near-Earth Object Survey mission, developed under the Planetary Defense Coordination Office, which the agency established in 2016 to formally coordinate this work. Note the date. A dedicated office for planetary defense is younger than most of the phones people are watching this on. Now suppose one day we find something, and the cone of uncertainty closes on us instead of away. What then? The answer is no longer theoretical, and this is genuinely the most important thing that has happened in this field. On September 26, 2022, 3 days before the AP7 paper was published, NASA's DART spacecraft deliberately collided with Dimorphos, a small moon orbiting the asteroid Didymos, at roughly 6 kilometers per second. The purpose was to test whether a kinetic impact can measurably change an asteroid's orbit. It worked, and it overperformed. The orbital period of Dimorphos around its parent body was shortened by roughly 32 minutes. The predefined threshold for calling the mission a success was 73 seconds. The result exceeded it by more than an order of magnitude, largely because the impact ejected a huge plume of material, and that ejecta acted like a rocket exhaust, pushing back on the asteroid far harder than the spacecraft alone could have. Here's what this means. Humanity has demonstrably altered the orbit of a celestial body on purpose. That capability did not exist before that date. It exists now. But be clear-eyed about the limits. DART worked because it targeted a small object with an orbit we could measure precisely from Earth, using a technique that produces a tiny velocity change. A tiny velocity change is enough, if you apply it early. Nudge an object years or decades before a predicted impact, and the deflection compounds across the entire remaining orbit until a hit becomes a miss. Apply the same nudge weeks before, and you've changed nothing that matters. Deflection is not a weapon you fire at an incoming rock. It is a technique that trades time for effectiveness, which means the single most valuable asset in planetary defense is not a spacecraft. It's warning time, which means the single most valuable investment is exactly what found 2022 AP7 in the first place. Surveys. And an object 1.5 kilometers across is a fundamentally harder problem than Dimorphos. The mass scales brutally. Deflecting a kilometer-plus object would require either far more energy or far more lead time, or both. It is not a scenario anyone has demonstrated. It's a scenario that depends entirely on finding the object decades ahead, which loops directly back to the blind spot, and to why 50 uncatalogued objects concentrated in the sun's glare is the number that should hold your attention. There's one more thing worth understanding, because most people assume nobody is watching. Somebody is, and the system is more organized than you'd expect. When any observatory anywhere on Earth spots a moving object, the measurements go to the Minor Planet Center, operating under the International Astronomical Union. That's the clearinghouse, the single global address where positional data lands. It's the reason a discovery in Chile can be confirmed by an amateur in Australia within hours. The object gets a provisional designation, and that designation encodes the date. 2022, AP7, tells you the year of discovery and the half-month within it, before you know anything else about it. From there, orbit determination software takes over, and impact monitoring runs continuously and automatically. NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory maintains an automated system that projects every known object's orbit a century or more into the future and flags any non-zero probability of impact. The European Space Agency runs a parallel independent system. Two systems, different code bases, cross-checking each other. When one flags something, the other's result is the first thing anyone looks at. And when something does get flagged, there's a public scale for it. The Torino scale, running from 0 to 10, combining impact probability with the energy involved. Almost everything that has ever been flagged sits at 0. A handful have briefly touched 1. Then more observations arrive. The uncertainty region shrinks. Earth falls outside it, and the object drops back to 0 and gets removed from the risk list entirely. Here's what this means. The machinery works, and it works transparently. The risk lists are public, updated automatically, and anyone can read them. But every part of that machinery depends on the same first step. Something has to be detected before any of it can run. An object nobody has ever imaged has no designation, no orbit solution, no probability, no Torino number. It is not low risk. It is unmeasured. And unmeasured is not the same thing as safe. So here's where we actually stand. Stripped of drama, 2022 AP7 is real. It is roughly 1.5 kilometers across, with a stated range of about 1.1 to 2.3 kilometers. It was found by a twilight survey led by Scott Shepard using the dark energy camera on the Blanco telescope in Chile and published in the Astronomical Journal on September 29, 2022. It crosses Earth's orbit, which classifies it as potentially hazardous. It does that crossing while Earth is on the other side of the Sun, and that pattern is expected to hold for centuries. It has no chance of hitting Earth currently, according to the astronomer who found it. Its long-term behavior is not precisely known, and no one is claiming otherwise. That is not a story about an asteroid that's going to hit us. It's a story about how close we came to never knowing it was there. Because the asteroid didn't change. Our knowledge did. On the day before the announcement, 2022 AP7 was on exactly the same orbit, moving at exactly the same speed, carrying exactly the same energy. And every risk assessment on Earth was silent about it. The only thing that changed was that someone pointed a 4-meter telescope at the horizon during a 10-minute window and looked into the light. The one takeaway, if you keep nothing else, the danger has never been the objects we've catalogued. Every asteroid with a name, a number, and a known orbit is, in the most literal sense, solved. It's the uncatalogued ones. And we now know, from the people running the surveys, that the ones still missing are concentrated in the one direction we struggle most to see. The blind spot is closing. Infrared space surveys, wider ground-based cadence surveys, and a demonstrated deflection capability all landed within the last few years. But the closing isn't finished, and every additional object pulled out of the glare is a permanent, irreversible reduction in the risk we all carry. Subscribe, because we track this as it develops. New recovery data, refined orbits, and every new object the twilight surveys pull out of the sun's glare. And if the idea of something that size going unnoticed unsettles you, wait until you see what happens in April 2029, when an asteroid large enough to be visible to the naked eye passes closer to Earth than our own communications satellites. And every telescope on the planet will be watching. That one's next. No guessing, just the facts.